Hello, everyone. So today we're going to be continuing our conversation on thermodynamics. So last time we were able to look at thermodynamic systems under both isobaric and reversible isothermal conditions. So we've now been looking at constant temperature, constant pressure. Guess what? There's only one real other thing we can hold constant. Today, it's time for isochoric. So let's go ahead and start with a quick recap of what we've addressed so far. So when looking at the thermodynamics of a system, it's always useful to start with the first law. So our change in energy is going to be related to the heat and the work entering and leaving the system. Now, one of the important things we discovered last time was a useful equation for the work of a system being related to the external pressure. So this is essentially going to be what pressure is going to resist any work done by the system, with the change of the system occurring from the change in volume. So this is often referred to as PV work. However, if I'm trying to examine the change in energy and specifically the change in heat of the system, we want to try and make our work expression as simple as possible. So what conditions are going to make this simple? Well, turns out I already gave you the hint. Isochoric conditions. Because what happens if we hold the volume change as constant? Well, then dV goes to 0. So then my work expression goes to 0, and we get a beautiful set of conditions. Turns out, if you're trying to simplify an equation, a good place to start is trying to figure out what can go to 0. So when we go ahead and do this, this gives us a relatively simple set of equations for our change in internal energy. Simply put, all of the change in internal energy is going to be due entirely to any addition or removal of heat. Or if we want to go ahead and put this in a more classic discrete formalism, again, the heat added into the system will be equivalent to the change in internal energy, again, under isochoric conditions. So one of the things that is often useful to think about it is if I go ahead and add a certain amount of heat to the system, as we've seen before, heat can be a path function, but internal energy is going to be a state function. All it cares about is our initial and ending conditions. So one can imagine that we can define this state function based on a limited set of conditions under which heat can be transferred. So this is actually going to be a fairly useful metric, because sometimes we're going to have a little bit more knowledge about our internal energy and we can use it to solve for our heat. But sometimes we'll be able to control the conditions at which we add heat to be able to accurately determine our internal energy. So one of the things we can end up using this for is using our we can use any change in heat of the system to be able to accurately measure the change in internal energy of an isochoric system. So this is going to be a very useful feature. Now let's go ahead and try and think a little bit more on what's going to be happening inside our chamber, which generally we like to make sure it's simple. So let's assume that our chamber is just filled with an ideal gas. I go ahead and heat the system, meaning I'm adding a set amount of energy to the system. Well, our key question at this point is, where can this energy go? So as we've talked about before, our internal energy can be subdivided into two categories: kinetic or potential. In this case, if it's an ideal gas, it doesn't have any intermolecular forces, and Lord help me if it's moving under gravitational, magnetic, or nuclear conditions. So at this point, there really isn't anywhere for the potential energy to change. So all that leaves us with is the kinetic energy. And for that, we have our good old friend, that it turns out that most of that kinetic energy can be well represented by temperature, because we've already seen a certain proportionality between our between our internal energy and the temperature or kinetic energy of the system. So because we have a certain proportionality between these terms, we end up giving that a constant. So and we call this our isochoric heat capacity. Heat capacity because it tells me how much heat it takes to change my temperature by 1 degree. And isochoric because, again, remember, we're assuming isochoric conditions to get this relationship. So let's go ahead and try and think about what this would look like more in a set of discrete terms. Because if I want to go ahead and relate this to a temperature change, well, I'm going to have to integrate it over the system. And oftentimes we're very lucky and our heat capacity won't change with temperature. And if that's the case, we get to use the expression that we used in general chemistry, that our change in internal energy is simply going to be equal to our heat capacity times our change in temperature. But this ends up more or less just kicking the question down the road, because we might be able to measure our change in temperature, but we might have a few more problems of measuring our internal energy. So in order to get this kind of relationship, we're going to want to try and determine what the heck my heat capacity is going to look like. Well, let's go ahead and start with kind of the smart-ass answer of more or less, we can rearrange our earlier equation and say that it literally is going to be the change in internal energy as we change temperature for constant volume conditions. Yeah, they told you it was a real smart-ass answer. But it turns out that this can actually be fairly useful, because it turns out if I can get a temperature-dependent expression for my internal energy, I can go ahead and get my heat capacity. Now, this might actually be troublesome for most materials, but it turns out that this is actually a pretty easy problem to solve for an ideal gas. Because as we saw already, for an ideal gas, all of our internal energy is kinetic. And it turns out we know a good set of equations for the kinetic energy of an ideal gas. So if I've got a monatomic gas, it turns out we can give our internal energy as 3/2 nRT. Now, some of you might have an idea where this came from, but let's go ahead and walk through it. So we determined that the kinetic energy of an individual gas molecule was 1/2 kT for each degree of motion. If I have a monatomic gas, all I have is 3 translational degrees of freedom, each one giving me 1/2 kT. Now, it turns out internal energy is a size extensive property, so I need to go ahead and turn this into account for the number of moles of gas I have. And again, when we go from a molecular to a molar basis, we go from kT to RT. So what we're really seeing is that for every mole of gas we have 3/2 RT, which with each half of the energy coming from one of our translational degrees of motion. Now, this gives me an expression that relates my internal energy to my temperature. So what we can then do is take the first derivative, and when we do this, we find an isochoric heat capacity of 3/2 nR, because, again, I can pull out the 3/2 nR as a constant, and the dTs cancel out. So this is actually a fairly cool feature that we can, from first principles, predict the heat capacity of any monatomic gas. However, this only gets us so far because it turns out we can only study noble gases so long before we start to get a little bit bored. So let's say I want to scale this up to diatomic gases, which ends up being rather relevant as the 2 most common gases in the atmosphere are both diatomic, oxygen and nitrogen. So in these cases, I get an extra 1/2 kT of motion from my 2 rotational degrees of freedom, which gives me an internal energy on the macro scale of 5/2 nRT, or a heat capacity of 5/2 nR. And indeed, sometimes I even get bored of working with nitrogen and oxygen. I have no idea why. They're fascinating gases. And I might want to even get to a nonlinear system, so something like water. In this case, we can generally predict our internal energy as 3 nRT because we have 6 degrees of freedom, each giving us a half kT of energy. We have our 3 translational motions and then our 3 rotationals, where I can rotate about the y-axis, the x-axis, and the z-axis. So when we do this, we can take our first derivative and get a heat capacity of 3 nR. So it is worth noting that sometimes this system will break down a bit and we have to go to the more general form. And the reason these expressions tend to break down is they assume that we're behaving as an ideal gas, which, ignores any behavior of liquids and solids. And second of all, ignores any vibrational motion because it turns out molecules can vibrate too, and they will add a little bit of noise to our heat capacities, which is worth acknowledging. But in general, we can always fall back on these two simple relationships of my heat capacity simply being the first derivative of my internal energy with temperature. And then again, if we have the heat capacity, we can turn this both to heat under isochoric conditions and into our change in internal energy. Now, again, one of the things you have to watch out is that real systems are messy. And it turns out because of these vibrational motions that most of the time heat capacity itself is going to show a certain degree of temperature dependence. And you can see this with a typical plot of internal energy versus temperature. Well, if we're working under fairly short temperature regions of, say, 100 degrees, we can treat our heat capacity as being fairly constant. But you may notice the slope of our internal energy does start significantly changing as we go to larger temperature differences. So if you're working with large temperature differences, you're often going to need to determine your heat capacity experimentally and pay very close attention to what temperature it was determined. So if you make use of typical chemical information tables, these will most commonly be reported at room temperature, but sometimes under more high or low temperature conditions, depending on what your material is being used for. So with this, we've been able to build up a series of very useful equations for describing heat, internal energy, and work, which should be fairly useful to proceed in the future. So as a quick review, if we know we can relate our change in internal energy to both the heat and work entering the system. This is our good old friend, the ideal gas. And for most of the conditions we're working with, we're going to be focusing in on all of the work occurring through what's called our PV work, which is going to focus just on expansion and contraction of our system. It turns out, however, if we can't measure our heat directly, we might be able to determine our internal energy along with our work through simple predetermination of our heat capacities and a measure of any temperature change. So hopefully being able to use all of these equations together, you might be able to get some real information about how heat, work, and work can pair together to really control what the energy is inside a simple gas phase system. So next time, we're going to focus a little bit more on the practical considerations of trying to determine heat capacity for real substances by talking about our good friend, bomb calorimetry. Till then, take care.